Okay, so good morning. Welcome to the last lecture on functional programming. So before I forget, today is the last lecture. Next week on Monday the 9th, I think. Let me check. Yeah, so on Monday the 9th and on Wednesday 11th, there will be no lecture and no exercise course. And the last exercise course will be on Friday the 13th. So this is the last lecture, and what will we do today? We will finish type checking for Haskell. So what did we do in the last lecture? We introduced the concept of type schemata. So what was a type schema? A type schema was something like a type, but you can have quantifiers. So it would be something like this for all a dot a, or maybe also something like this, where some type variables are quantified and others are not quantified. So for all a dot a goes to list b or whatever. So things like this are type schemata. So like types, but you may have quantifiers. And what is the type assumption? And the idea is we want to make explicit which type variables can really be instantiated completely arbitrarily. That's the reason for this universal quantifier. Now, a type assumption is something like an environment. So the type assumption tells us what we already know. So there are certain variables, there are certain predefined operations, and for them we already know what type they have. So a type assumption is a mapping, and this mapping maps variables and constants, and this contains in particular the predefined operations and the data constructors. They are mapped to the set of type schemata. And there's an initial type assumption which tells us for the predefined operations and the variables and the data constructors what their type is. So the initial type assumption was called A0, and we start with this initial type assumption and then we extend it. So this was called A0, and for example, if we have a variable, then we know that variables can have arbitrary type. So the type schema for such a variable would be for all a dot a, for all variables x. But if we have something else, for example, if we have, let's say, a predefined operation like not, well, here the type schema would be, it's a function from bool to bool. Or if we have something like cons. So cons is a data constructor for lists, which we have probably predefined. Well, then the type of cons would be something like you take an element of type A, you take a list with elements of type A, and you get a new list with elements of type A, and here A is universally quantified. So this is the initial type assumption. And now the goal was to define an algorithm for type checking. Unfortunately, the overhead projector is not working anymore, so we have to do this without slides. So the goal is we want to define a function for inferring types, and this function was called W for historical purposes. And what does this W do? So this W algorithm gets two inputs. One input is the type assumption that we have. So this type assumption has some information on the types of constants and variables, and this can be a partial mapping. So I should mention this here. So the mapping can be partial. So it doesn't need to know the type schema for every variable and for every constant, but at least for some. So for some variables and constants, we know their type already. And this is the term t whose type we want to check. So the question is this term well typed if we know these type assumptions? And if it is well typed, what is its most general type? So the result should be the most general type of t. So this is the most general type of t. And moreover, it can turn out that in order to make t well typed, we have to refine these type assumptions here. We have to instantiate free variables in these type assumptions in a certain way. And so the second result here is some substitution theta. So this is a substitution. And a substitution such that t is only well typed if the current type assumption A is refined to the type assumption A theta, where all the free variables in A are instantiated by theta. We will see this, how this works today. And so this is the goal, to define this, and we want to define this for all lambda terms. Now, lambda terms are either variables or constants or applications or lambda abstractions. So these are the cases that we have to consider. And in the last lecture, we already considered the first case. And the first case were variables and constants. So case 1 is t is a variable or a constant. And then we already said how to define this. Now, so suppose we have, so in other words, t is some constant c or some variable c. So if we want to find out what is the type of c, well, then we just look into the type assumption. And the type assumption should tell us what the type of c is. So the type assumption should look like this. It should say that c has a certain type schema, and the type schema should look like this. So there should be lots of universal quantifiers here, a1 to an, and then a type tau. So this means this whole thing is the type assumption where c has this type schema, and for all other variables and constants, we have to look in A. So this plus means the information on C, which might be in A, is overwritten, and the information for C is now this one, and for all other variables and constants, we look into the type assumption A. So we know that C has this type schema, and so the resulting type of C should be tau. So first, there is no need to refine the type assumption further because C is already well typed. So here we just refine it further by the identity, which means we do nothing. And the type of C, well, the type of C is tau, but these type variables a1 to an, they can be instantiated arbitrarily. And in order to avoid conflicts, because a1 and an are probably used somewhere else already, we rename them by fresh type variables. So we replace a1 by a fresh type variable b1, and we do the same thing for a2 till an. So where b1 to bn are fresh variables. So this is what we did already in the last lecture. Now case 2 is the case where t has the form has the following form. It's a lambda abstraction. So it's a lambda abstraction of the form. I shouldn't write it like this. I should. Let me just write T is a lambda abstraction. So T is built with a lambda. So T is a lambda abstraction. And this is a bit complicated because we already looked at an example in the last lecture. So if you look at the following example, this is the one that we looked at in the last lecture, lambda f dot. So this is the function that takes an f and maps it to the stuff behind the dot. And here we want to add, so we use plus, f applied to true and f applied to 3. And now the question was, is this well typed? And well, the problem is if this were well typed, what should be the type of f? So what's the type of f? The type of f, well, it should be applicable to Booleans and to integers. So it must be applicable to anything. So the type of f must take an arbitrary input of an arbitrary type A, and it has to return something of type int, otherwise I cannot apply plus to it. So it should have the type A to int. And, well, if you think of type schemata instead of types, then this means this A has to be universally quantified because I can really instantiate this A arbitrarily. I can instantiate it with bool, and I can instantiate it also with int. So the type schema of f should be this. And, well, the type of this thing will be int because plus takes two integers and returns an integer. So in other words, this would have the following type schema. So, well, it's a function that takes something of this type and returns an int. So it takes something of this type for all a arrow int, and it returns an integer. And so this is a type schema where the universal quantifier is not at the very outside, but it's inside in this premise here. So it must, this term would only be applicable to functions which themselves can take arbitrary inputs. And type schemata like this are called non-shallow. So a type schema is shallow if all the quantifiers are at the beginning, so at the very outside, and after that there are no further quantifiers. So this is a non-shallow type schema. And something like this is not allowed in most programming languages and also not allowed in Haskell because they make type checking very complicated and probably even undecidable. So this is not allowed in Haskell. Which means that Haskell would consider this term as not well typed. So what's the problem? The problem is as soon as we have a lambda, we have this restriction. So what does this mean? So this means that every lambda abstraction of the following form so every lambda abstraction which looks like this, lambda x dot t, if this is well typed, then it must have a type schema of the following form. Well, this x must have some type tau1, and this t must have some type tau2. And so the whole thing is a function from tau1 to tau2. So it's a function from tau1 to tau2. But all the type variables in here, they have to be quantified at the very outside. So it should look like this. If I write the universal quantifier without variables, then this means this is the universal closure. So all the type variables in here, they have to be quantified over here. This is just a shorthand notation which we introduced in the last lecture. So this means for all instantiations of the type variables in here, so I can instantiate the type variables in tau1 arbitrarily, and no matter how I instantiate them, this function should be applicable to the argument. So one can instantiate the type variables in tau1 the type variables in tau 1 arbitrarily. And if one does that, then still lambda x dot t will be applicable to the argument where we instantiated these type variables arbitrarily. But this also means that if we instantiate the type variables of tau 1 in a certain way, so that in other words, x gets a certain type which is more special, more specific than tau 1, then x must have the same type everywhere in t. So if x occurs several times in t, it must have the same type everywhere. So that's the important observation we have here. So if x occurs several times in t, then all occurrences of x must have the same type. So the type variables in tau 1, they can be instantiated arbitrarily, but they have to be instantiated in the same way for all occurrences of x. So then all these occurrences of x have the same type. And so this means so this means if I have something like this, lambda f plus f of something, well then here f has arbitrary type in the beginning. So f at first has an arbitrary type of the form a goes to int, because I mean f has to return an integer here, but f can be applied to anything. But if I instantiate this a in a certain way, for example by bool, then a has to be instantiated in the same way both here and here. But if a is instantiated for example by bool, then all occurrences of f in the body of the lambda term, so here and here, and the body of the term, and I mean here and here, must also have the type, well, if a is instantiated by bool, then they must have this type bool to int. So in other words, if f is bound here by a lambda, then this means you can instantiate the type variable arbitrarily, but then this instantiation has to be used all over for all occurrences of f in the body here. So it's not possible to apply f to an integer and to a Boolean here. You can apply it everywhere to an integer or everywhere to a Boolean, but not mixed. And this is the special case of the lambda. It's different if you define f in a separate declaration. So we've seen that this f term up there is not well typed, but if we look at the following, so let's for example say this. So now f is the function that takes an argument and maps it to the number 1. So the argument is simply disregarded. And now we write again the same nasty term here, so f true, f3. What about this? So this plus term here is the same term that we had up there in the body of the lambda term. So this plus term is the same as this plus term. But here f is bound by a lambda, and here f is bound by a let. And here I even defined f concretely. So is this well-typed or not? Can you write this in Haskell, and will Haskell accept this or not? So up here we realized Haskell does not accept this. What about this? So here f is just an abbreviation for this function. F takes an arbitrary argument and maps it to 1. So can you apply this f to true? Is this well-typed? Sure. I mean, what's the type of f? The type of f is, it takes an arbitrary argument of type A, and it returns 1, so it returns int. Right? So this and this A can really be instantiated arbitrarily. So yes, you can apply this to any argument, and it gives you 1. And of course you can apply this f to true. This will give you 1. And of course you can apply it also to 3. This will also give you 1. And so this expression here is well-typed, and it will evaluate to +1, 1 to 2. So yes, this is well-typed. So what's the difference? The difference is that here, this f has a separate declaration. It's a local declaration here. It could also be a declaration on top level. In both cases, f would have this type. And, well, if f has this type, then, of course, you can apply f to Booleans and to integers. That's not a problem. So different occurrences of f may use different instantiations of this type variable. So this is true if f has a separate declaration, but it's not true if f is bound by a lambda. If it's bound by a lambda, then you can instantiate this arbitrarily, but once you instantiate it, you have to use the same instantiation for all occurrences of f. So this is well-typed. So here one can use different instantiations of f, instantiations of A for different occurrences of f. Because we need no non-shallow type schema to express this. F has a shallow type schema, namely this one. And, well, this thing has type int, so this is extremely shallow. So this is something which is surprising at first sight. But now that we know this, we can think about how to compute the types for lambda abstractions. But I guess I have to wipe this board down here first. Yes?
This is no lambda expression. So if you say
yes, okay, it's no lambda expression, that's true. This is Haskell. So this would be translated into a complicated looking lambda abstraction. In fact, what would happen is that we would substitute lambda x dot 1 both here and there, essentially, which is okay. So yes, it's Haskell, and it would be translated to a lambda expression, which would then be well-typed as well. Correct. But I wanted to make clear also on the Haskell level, I mean, in Haskell you can write this if you replace lambda by backslash, and you can write this if you, okay, this is a strange mixture, you're right. So if this is Haskell, then you would have to write backslash instead of lambda. Okay, but, okay, you're right. But to illustrate the problem, I think you can abstract from backslash and lambda and identify these similar looking symbols. Okay, let's now continue with this algorithm and come up with the rule how to do type checking for lambda abstractions. Okay, to derive the definition of the W algorithm for lambda abstractions, let's look at an example. How can we infer the type of a lambda abstraction? So let's look again at an example. And let's, for example, take the following one. Lambda x dot cons 0 cons xx. And cons is defined by a user-defined data type. It should be the data constructor for list insertion. So the type schema for cons is this one. You take an element, you take a list, and you return a list. So what's your guess? Is this well-typed? And if yes, what is its type, or is this not well-typed? I mean, the algorithm should find this out automatically, but it doesn't harm if we think about it before. Yes? It's not well-typed, and why not? Yes? And 0 is no list. Yeah, but that doesn't matter. I mean,
yes, it does because you have list A. So cons takes an A.
Yes?
And a list A, and this has to be the same A.
True, but then, I mean, you could instantiate A by int. I mean, 0 has type int, so cons 0, cons 1, nil would be perfectly well typed. No?
X cannot be 1. X is the list.
Right, okay, yes, you're right. So this 0 means that we have a list of integers. So this x must have type integer, but this must be a list. So it cannot be both an integer and a list, so something goes wrong here. And of course, at first sight, you could think, well, x has arbitrary type, but because it is bound by a lambda, it must have the same type everywhere in here. So if I decide to instantiate the type variable here, this type variable a, by int, then I cannot instantiate it by a list of something. So without this lambda, so this thing would be well typed. Because here x is an arbitrary variable. If it's a free variable, I can instantiate it in any way I like, but as soon as I add this, I have a problem. Now it's not well typed anymore because this means all occurrences of x must have the same type. Okay, so it's not well typed, and well, the algorithm should detect this. So at first, x can have an arbitrary type. So here it can still have an arbitrary type. B. And so that means what we want to compute is we have some type assumption A, and we want to find out what is the type of lambda x, well, cons 0, cons xx. And, well, the algorithm now should take into account that x has an arbitrary type, but it should have the same type everywhere. And so it should have the same type B everywhere. And the trick is we call this W algorithm recursively, but we modify the type assumption for x. Up to now, the type assumption for x was it can have anything. Every occurrence of x can have a fresh type. So it had the type schema for all a.a. And now we say, OK, x can have an arbitrary type, but it cannot be instantiated differently if we have different occurrences of x, but all the occurrences must have the same type. And the trick is just to omit the universal quantifier. So x has some type b, but b is not universally quantified. And this means I can later on refine this. I can instantiate this b, but then b will be instantiated in the same way everywhere. So my type assumption is now x has type b, but not for all b.b, and the rest is like in A. And now I check what's the type of this body of the lambda abstraction. Cons xx. And, well, what will I find out? If I know this, then I will find out that this x, well, what's the type schema for x? Under this type assumption, the type schema for x will be b. And under this type assumption, the type schema for this x will also be b. And, well, then I will have a problem because it will turn out that, well, this has the type int. And then, indeed, I will find out that, well, this int requires b to be int, but then we have a conflict over here. or otherwise this x requires b to be list of something, but then this cannot be int. And so here we get a conflict because b cannot be instantiated to, well, both int and list of int. And therefore, because we now have extended this type assumption and have said, well, x has the same type b everywhere, this shows us that type checking will go wrong here because these two x's need to have the same type. Let's look at another example. Now this time let's look at the example lambda x dot tuple2 xx. And what is tuple2? Tuple2 is one of the predefined functions which takes two objects and returns the tuple of these two objects. So what's the type assumption for tuple2? The type assumption is it takes something of type A, it takes something of type B, and it returns a pair of type A comma B. And A and B can be instantiated arbitrarily. Now, is this well typed? So again, two occurrences of x, so this always looks dubious, but this time this is really completely harmless. I mean, why shouldn't you build a pair with twice the same component in there? I mean, a pair like 2, 2 or nil, nil, that's perfectly acceptable. So yes, of course, this is well typed. So how would we determine the type of this? So if we want to determine the type of this, we would again do the same thing. So currently x has arbitrary type, but this lambda x means all occurrences of x in here must get the same type. So to compute this, we would first compute the following. We would extend the type assumption as follows. We would say, well, x now has some arbitrary type b, but the same type everywhere. And under this type assumption, we now determine the type of tuple xx. And well, how this will be done, we will see when we discuss about type checking for applications. But it's pretty clear what is the result. If this has type B and this has type B, what will be the type of tuple2 xx? Well, if tuple has this type, if you apply it to two arguments of type B, then the result will have the type B comma B. So this whole thing will have the type B comma B. So this is the outcome here. This thing, under this type assumption, this term is well typed and it has this type. And did we have to refine the type assumption to make it well typed? No. I mean, we just took this type assumption and everything was fine. So no refinement is necessary. And so to compute this, we wanted to compute that. And now since we know this, we can find out what the type of lambda x tuple xx was. So this refers to this. Well, this should be a function where x is mapped to tuple2 xx. And well, what did we have to do? We had to, the result here is BB. So the result here is BB. But it should now, of course, be a function. And here we assumed that x has type B. So this x has type B. And if x has type B, then the whole thing has the type tuple2 xx. So this term should have this type. B goes to B comma B. And did we have to refine the type assumption in any way? Well, here no refinement was necessary, so no refinement is necessary. So that's the idea. If we have a lambda abstraction like this, we assume that X has some arbitrary type B. We compute the type of the body of the lambda abstraction, and then the type of the whole thing is B, arrow, and then the type of the body. And that indeed makes sense. I mean, if you look at this, this is the type you would expect. Now let's look at one more example, because up to now you might ask, what is this refinement necessary for? What is the substitution necessary for? So let's look at an example where this is needed. And then we define this W algorithm also for lambda abstractions. So now, one more example. Let's try to find out what is the type of the following term, lambda x dot plus xx. So again, two occurrences of x, so this looks dangerous. Is this well typed? Yes, of course. And now if you look at this intuitively, what's the type of this? Int. Well, no. I mean, if a lambda stands there, then the whole thing doesn't have type int. It should be a function. From int to int. It should be a function. It's the double function. It takes a number and gives you back this number plus this number. So you can apply it to 7 and you get back 14. So this is the double function and it has the type int to int. So we expect that this is well typed and the type should be int to int. Okay, so that's what we expect. And so the algorithm should give us this. So what does the algorithm do? It says, aha, there is a lambda here. So at first, I just know X has some type B. I don't know which type, but it should be the same type everywhere. So under this assumption, I now check plus XX. Now plus XX, and now we find out that to make this well typed, I mean, this has type B. This has type B. But this has the type int to int to int. So to make this well typed, we have to refine the current type assumption, because you cannot apply plus to something of an arbitrary type B. You can only apply plus to int arguments. So now we have one of the cases where the current type assumption is not strong enough to allow this application. But in fact, this thing is only well typed if we refine this type assumption further and replace B by int. So now it turns out that to make this well typed, this type assumption is not enough. But here we have to do a refinement. We have to replace B by int. We have to instantiate B by int. So this is the substitution which substitutes all three occurrences of B by int. If we do this, then, well, this has type int, this has type int. We apply plus to it, and then the whole thing has the type int. So this is this substitution theta, which we need to refine our current type assumption. And so now we have found out this body here is well typed if the type assumption is refined like this. So then what's the type of this? Well, we have seen that we need this refinement to make everything go through. So B has to be instantiated by int. And what's the type of the whole thing? Well, it's the function from the type of x to the type of plus xx. So the type of x was B. And what's the type of plus xx? Well, that we determined just here. It's int. But in fact, the type of x should not be B, but the body here is only well typed if B is refined like this. So this substitution theta should be applied to B. So it should be B theta. In other words, it should be int. Because only if we refine the type assumption by this theta, only then is the body well typed. So if B is refined like this, then the body is well typed, and so the type of the whole thing is int to int, which is what we expected. Yes?
Why did you apply int theta to B now?
because we have seen that B must be int, otherwise this body is not well typed.
But why do they apply theta now? I mean, we have the substitution that says this is only well typed if you apply the substitution, but we have already applied it, so it's already well typed.
No, I have applied it when I determined the type of the body, but I haven't applied it to the type of this x up here. Because only when I look at the body, I find out that this shouldn't have type B, but this should have type int. So let me write down the general rule for W, and then we can reconsider this again and see whether we are happy with that or not. So this part of the blackboard should be the definition of W. So what happens if I want to find out what is the type of lambda x dot t? Well, what I do is I call W recursively with this new type assumption where x gets type B, and I determine the type of t. And the result of this is some theta and some tau. And here B is a new variable. So I find out that the type of the body term here is tau, but this is only correct if this type assumption is refined by theta. So in other words, this thing is only well typed if A is refined by theta, and then of course x does not have type B, but then it has type B theta. So this is the function from B theta to tau. So that's the result here. It's a function from B theta to tau, and to make this work, I have to refine the type assumption A by theta. So that's the definition of the W algorithm for lambda abstractions. And you can see it's a recursive algorithm. So in order to determine the type of this, I call W recursively with this term here, but termination of this algorithm is pretty obvious because the terms get smaller. I mean, here we have omitted this lambda x. So is it? So now we go back again.
Why do you don't need just B to tau?
Because it's wrong. I mean, if we have found out that this is only well typed if we don't have B, but we have int instead. So if we find out that here the type is B to int, then that's the wrong type, because this may not have an arbitrary type B. But B must be int.
So you want to have tau as a fixed type and not to refine it by theta afterwards?
Well, tau is already refined by theta. We took theta into account when we determined tau, but we didn't take theta into account when we decided on this type variable B, because at that time we didn't know theta yet. So therefore we have to repair this mistake afterwards. Okay, now we know how to get the type for constants, variables, and lambda abstractions. So the missing part are applications. So case 3 is T is an application. So something of the form T1 is applied to T2. So how should type checking work for applications? So what's the type of T1 applied to T2? Now to make this work, an obvious approach is let's first determine the type of T1 and let's determine the type of T2. So this should have a type tau1, and this has a type tau2. And when is this well typed? Well, this is well typed if tau1 is a function which expects an argument of tau 2, right? Because, I mean, this thing should be a function and it's applied to this argument. If tau 1 corresponds to, whatever corresponds to means, corresponds to a type of the following form, it's a function that takes an argument of tau 2 and it returns the result of some arbitrary type tau 3. Right? If this has the form tau 2 arrow tau 3, then clearly I can apply it to arguments of type tau 2. Now, this corresponds to, I mean, the problem is again polymorphism. What happens if we have type variables here? So let's look at an example. What about the following term, cons 0? Is this well-typed? And if it is well-typed, what is its type? So let's first look at this intuitively and then see how to compute it. So what's the type of cons? Well, the type of cons, so let's compute the type of cons first. So what's the type of cons? Well, the type of cons is, it's a function. So to compute this, I don't have to refine the type assumption. I just look into the initial type assumption. And this tells me the type is something like this. E goes to list E goes to list E. For some fresh type variable E. And what's the type of 0? Well, the type of 0 is int, and I also don't have to refine the type assumption anyway. So this is tau 2, and this here is tau 1. And now the question is, does tau 1 have the form tau 2 arrow something else? Now, if we have many of these arrows, this always associates to the right. So this stands for this. And yeah, clearly this corresponds, because this is a function that takes an arbitrary input type E and gives me back a function from list E to list E. And well, if I can take an arbitrary input type E, I can also take, I can instantiate E by int, and then this thing indeed is well typed. So the question is, to find out whether tau 1 corresponds to something like tau 2 goes to tau 3 for some tau 3. Well, since tau 3 is not really, there's no restriction on tau 3. Tau 3 can be anything. So let's assume it's a fresh type variable, and then let's see how this type variable has to be instantiated to make things work. We start with assuming that tau 3 is something arbitrary. So fresh type variable. And then the question is, can we make this equal? So can we make tau 1, which in our example is E goes to list E arrow list E. Can we make this equal to tau 2 arrow tau 3? What is tau 2 arrow tau 3? Well, tau 2 is int, and tau 3 is an arbitrary type variable. So this is tau 2, this is tau 3. And the question is, can we instantiate the type variables here in such a way that this and this becomes equal? So can we instantiate E and B in such a way that they become equal? So in other words, can we instantiate the type variables that we have here, so E and B, E and B, such that these two types become equal. Such that these two types become equal. And well, if we look at this very closely, then we see the solution. So, I mean, to make them equal, E and int have to be the same. So E must be instantiated by int. So the answer is yes. And, well, we take a substitution. What does the substitution have to do? It has to instantiate E by int. Now, if E is instantiated by int, then here we have list int, and here we have also list int. So to make these two things equal, we have to instantiate B also, namely by the function type list int goes to list int. So B must be list int goes to list int. And this question, can we make two expressions equal by instantiating the variables appropriately? This question is called unification. And what we do is we search for a unifier of these two types. So we try to find a unifier, and in fact not just any unifier, but we are interested in most general types. So we look for the most general unifier of these two types. The most general unifier theta of tau 1 and of tau 2 arrow B. So we assumed that tau 3 is B. And in our example, this exists. So we see that in order to make them equal, we have to instantiate the variables in this way. And this means if we instantiate the type variables like this, then this would be well typed. And then we also know what is the type of the result. So the type of the term is, well, what's the type of the term? So the type of the term is if we apply a function of type tau 1. Sorry, if tau 1 and tau 2 arrow tau 3 is the same, and we apply this function to something of argument tau 2, then we get a result of type tau 3. So in our example, we get something of type B as a result, but of course B has to be instantiated by this unifier. So the type of the resulting term is B theta, which means in our example, so in the example, the term cons 0 is indeed well typed. And it has the type, well, it has the type B theta, which is list int goes to list int. So this means cons 0 is a function. Indeed, it's a function. It's a partial application. It waits for the second argument of cons, and the second argument of cont must be an int list. And the second argument of cons is always a list, and that it's an int list we can see from this first argument here. So it waits for an int list, and it gives me back an int list. And this can be determined in this way. So let's define formally what a unifier is. And this concept of unification, this is a general concept that you need in many places in computer science. So it is needed to infer the types if you have polymorphic types, but it's also needed elsewhere. For example, in logic programming, unification is used for evaluating programs, and there are also several other places where unification is needed. So it's a general concept which you have probably seen before. but it doesn't harm to see it again. So here's so what's unification? Definition 422. So let theta be a substitution. And since here we are only interested in types, this means it's a mapping which maps type variables to types. A mapping from type variables to types, and this mapping should only modify the type variables for finitely many type variables. So where only finitely many type variables are not mapped to themselves. Where only finitely many type variables are not mapped to themselves. Are not mapped to themselves. And now what does unifier mean? So we say that the substitution theta is a unifier of two types, tau and tau prime. If it makes them equal. So if it instantiates the type variables in there in such a way that tau and tau prime become the same. If tau theta, so this means we apply theta to tau and we instantiate all the variables in the way that theta tells us. And this is the same as tau prime theta. And in general, there can be many such unifiers, and we are interested in those that substitute as little as possible. So a substitution theta prime is a most general unifier. MGU for short, of tau and tau prime. If we have the following, well, first of all, it must be a unifier. So it makes them equal. It's a unifier of tau and tau prime. And it must be more general than any other unifier. That means if we have another unifier, then this other unifier is a specialization of this most general one. So this means for all unifiers, so if we have another unifier, theta of tau and tau prime, we can get this other unifier by first applying the most general unifier and then applying something more, probably. So for all unifiers, there exists another substitution, delta. Delta such that we get this other unifier by first applying the most general unifier. So this was the most general unifier, and then applying something else. So this means this is the composition of two unifiers. It means first apply the most general one, first apply theta prime, and then apply delta. So to give you an example, So let's look at an example again. Up there, we've seen that so another unifier of tau 1 and tau 2 arrow tau 3 is in this example there are no two unifiers. So we need to make a fresh example to demonstrate the difference between most general and not most general unifier. So let's make another example. Cons bot. What's the type of this? So to find out the type here, again, we have to find out what is tau 1, what is tau 2, and, well, what is tau 1? Tau 1 is, again, E goes to list E goes to list E. What is tau 2? Well, what's the type of bot? The type of bot is arbitrary, so it's A. And so we have to unify tau 1 and tau 2 arrow B. So unify tau 1 and tau 2 arrow B. So tau 1, well, we see here. So E goes to list E, goes to list E. And this we have to unify with A arrow B. So what are the unifiers here? What's the most general unifier? So this theta prime. So how can I make them equal? So can I instantiate the variables A, E, and B in such a way that this becomes equal? Or is this not well typed, maybe? Yeah, I can instantiate that. So first of all, I have to make the stuff before the arrow equal. So E and A have to be made equal. How do I do this? Many possibilities. For example, I can replace E by A if I want. Then here I have A, there I have A, fine. Now then here I have list A goes to list A. And to make this equal to B, I have to instantiate B by list A goes to list A. List A goes to list A. So this is the most general unifier. Here I instantiated what I had to instantiate. And what's the resulting type of cons bot? The resulting type is B, and then we apply this unifier. So it's B theta prime, which is list A goes to list A. And indeed, this is what Haskell would compute. If you write cons bot, where bot has arbitrary type, then the whole thing would have the type. It expects a list of arbitrary type and returns a list of the same arbitrary type. But there are also other unifiers, which are not most general. So I can also make them equal by using this unifier. For example, let's say I instantiate A by int and E by int. This will make them equal as well. I mean, there is no real reason for instantiating them with int, but it would make them equal. So let's instantiate E by int, A by int. So now they are equal, and then here I have list int goes to list int, so B must be list int goes to list int. That should be B. So B is instantiated by list int goes to list int. And if I would take this non-most general unifier, then I would now infer that the type of the whole thing is B theta, so it would be list int goes to list int, and that's of course not the most general type. So the inferred type would be list int goes to list int. And I mean, that's not wrong because it's too special. This thing could have the type list int goes to list int, but it has an even more general type, namely list A goes to list A. And therefore, since we want the most general types, we look for the most general unifiers. And indeed, these unifiers have the connection that I wrote up there in the definition. So indeed, there exists a substitution delta such that I get this less general unifier, so theta. I can get this by first applying the most general unifier and then applying theta, and then applying delta. So how would delta look like in our example? How can I get this less general unifier if I first apply this one? Well, I can first apply this one, then E is replaced by A is not replaced at all, and B is replaced by list A arrow list A. But if afterwards I instantiate A by int, then I have the same thing that I have here. So in our example here, delta would be the following refinement. I would afterwards have to instantiate A by int. So if I first apply this, and then I apply this, so first this, and then this. Yeah, okay, it's standing up there. So if I first apply this and then this, I get this less general unifier where A and E are instantiated by int, and B is instantiated by list int goes to list int. So that's the concept of unification. And, well, we can already see in the example it's not very difficult to unify two expressions. I mean, we just have to make them equal. And indeed, unification is decidable, and there exist algorithms for that. So unification is decidable. There exist more and less sophisticated algorithms for this. And whenever two types are unifiable, there also exists the most general unifier. Whenever two types are unifiable, so they can be made equal, then there also exists a most general unifier. And the most general unifier is unique up to variable renaming. So here, for example, you could replace E by A, like I did, or you could replace A by E. So that would work in the same way, but it doesn't really matter. I mean, if you do it like I did it, then the resulting type is list A goes to list A, and if you do it the other way around, the resulting type would be list E goes to list E. So the names of the type variables, they could differ, but that's the only difference. So the most general unifier is unique up to variable renaming. And in fact, this unification procedure is pretty simple in the examples. So now thinking about this, we've almost reached the step where we can complete our algorithm W, but we still have to think about the refinement of type assumptions. So sometimes it can happen that we have to refine type assumptions. And so how would we proceed? So to compute the type of T1 applied to T2, well, we have seen we should first compute the type of T1 and of T2. So in other words, we want to compute, we have some type assumption A, we want to find out what is the type of T1 and T2. So first we compute the type tau1 of T1. So we compute this, and we find out this has the type tau1, but we also find out that to make T1 well-typed, we have to refine our current type assumption by θ1. So this could happen. Now, next we want to compute the type of T2. So we want to compute the type of T2. But now we already know that the type assumption A alone is not sufficient, because already to make just T1 well-typed, it has to be refined like this. So we already know we should not regard A, but we should regard A θ1. So we should regard this refined type assumption and find out, is T2 well-typed under this refined type assumption? And if this works out, we get the type of T2, but we might get another refinement of the type assumption. So at this point, if this all worked out, we know that the type assumption has to be refined first by θ1 and then by θ2. And if the type assumption is A θ1 θ2, then T2 has this type, tau2, and T1, well, T1 doesn't have the type tau1, but we still have to do this refinement, which we only determined afterwards. So at this point, now we know that the type assumption has to be refined to, well, θ1 and θ2. And we know that then T2 has the type tau2, and T1 has the type, well, not tau1, because when we determined tau1, we didn't know about θ2 yet. So we have to do this refinement as well. So it has the type tau1 θ2. So all the free variables, all the type variables in here, they have to be refined like we determined here, because otherwise the argument here is not well typed. So now we know the types of T1 and of T2, and now we have to do this unification. We have to find out, does tau1 or tau1 θ2 really have the form tau2 arrow something? So we now compute the most general unifier of the type of T1, which is tau1 θ2. And well, this should have a type which takes an argument of this type, so of type tau2, and returns some argument of arbitrary type B, where B is fresh. And if this all works out, then the result is, well, this is what we were interested in initially. Okay, and this MGU we call θ3. So now we find out the type of T1 applied to T2 is B. But of course, B has to be instantiated by this θ3 because, well, θ3 tells us how to instantiate all these type variables in here. Otherwise, the unification doesn't work. So the type of this whole thing is B θ3. And what is the refinement that we need? Well, we have already seen that A has to be refined by θ1, otherwise T1 is not well typed, by θ2, otherwise T2 is not well typed, and it also has to be refined by θ3, otherwise I cannot apply T1 to T2. So I have to do all these refinements, θ1, θ2, θ3. And then everything works out well. So let me write down the definition, and then we summarize this again in an example. So how does it work? We want to determine what is the type of T1 applied to T2. So we first determine the type of T1, which is theta1 tau1. Then we determine the type of T2, but we refine A already appropriately. So this is theta2 tau2. And now we compute the most general unifier of tau1 theta2 and, well, this should be a function from tau2 to some fresh variable b. And this MGU we call theta3, and b is fresh, is a new variable. And if this all worked out, then we know that A has to be refined by theta1, theta2, and theta3, and the result of the application is B with this unifier, so B theta3. So this is the W algorithm. So to illustrate it, let's apply it to an example. So let's take the initial type assumption, and we want to find out what is the type of this term, lambda x dot cons xx. Is this well typed or not? What's your guess? Then let's see. Okay, so we don't know. So we see there's a lambda. So to find this out, we first have to call W recursively, and x must have some type B, and under this assumption we now determine cons xx. Now to determine this, cons xx, these applications mean first we apply cons to x and then we apply to that. So according to the definition of the W algorithm, we next have to determine the type of cons x. So let's determine the type of cons x. And, well, to determine the type of cons x, it's again an application. So first I have to determine the type of cons. So what's this? Well, the type of cons, I can look into the type assumption. In the type assumption, I don't have to refine it. It tells me this has type E goes to list E goes to list E. I also have to determine the type of x, where the current type assumption has to be refined further by the identity. Well, so no refinement takes place. So the type of this is B, and no further refinement is needed. So now I know what the type of this is, I know what the type of this is, so now I have to do unification. So what's the unifier of this thing? E, list E, list E, with B arrow some fresh variable, so let's call it C, for example. And now I see what I have to do. I have to replace E by B, for example, and C by list B goes to list B. So E by B and C by list B goes to list B. So what I find out here is that cons x is well typed, but I need this refinement. I have to replace E by B and C by this thing. And then cons x has the following type. It has the type C, but C has to be instantiated like this, so it has the type list B goes to list B. Okay, now I get to this point. Now I know what the type of cons X is, namely this thing, and I have to find out what the type of X is. So what's the type of X? So, well, if I apply this thing, since E and B don't occur free in this type assumption, I still have A0 and X replaced by B. And I want to find out what's the type of X. So the type of X is B. And now I again have to do unification. So I'm now operating like a computer. I mean, I just execute this algorithm. So there's no creativity involved here. It's just execution of the algorithm. So what's the most general unifier of? Well, the type of cons X is this. So it's list B goes to list B. And list B goes to list B has to be unified with the type of the argument arrow a fresh variable. So it has to be unified with B arrow a fresh variable D. So what's the unifier of this? So essentially what I see here is if I look at cons XX, I mean, due to this lambda x, all occurrences of x must have the same type here. So they all have the same, some type B. And we've now seen that one of these arguments has type B and the other one has type list B. And we have to make that equal. We can see this here. I mean, to make these two types equal, the stuff before the arrow has to be equal and the stuff behind the arrow must be equal. So in particular, B and list B must be the same. And now we see that no matter how we instantiate B, this will never get equal. I mean, there's no way to make B and list B equal. If I instantiate B by int, then I have int and list int. That's not equal. If I instantiate it by something more complicated, still this will have more B's than this. So this does not exist. Does not exist. So something like B and list B cannot be unified. If you want to unify a variable with another term where this variable occurs, then this doesn't work. So this cannot be unified, and this kind of failure is called occur failure. And this shows that something goes wrong. And as soon as something goes wrong, as soon as some unification doesn't work, the algorithm stops and says, this is not well typed. I mean, if everything works through, then the term is well typed, and we find out the most general type. And if some unification goes wrong, then this is how the algorithm detects that the term is not well typed. So the result is the term is not well typed. So yeah, these type failures are detected by failing unifications. So non-well-typed terms are detected by failing unifications. So the guess was wrong. This thing is not well-typed, and it's clear. I mean, this must be a list of elements of some type B, and this is an element of type B, and this cannot be the same. So therefore, something like this cannot be well typed. Okay, so this algorithm really does what it should, and this is essentially the algorithm that Haskell uses for type checking. And well, now we have seen not only what the semantics of Haskell is, but also how Haskell can be implemented. We've seen how to translate it to some machine language like lambda calculus. We've seen how to evaluate it, and we've seen how to do type checking also on the lambda calculus. So you should have now some good idea of, well, what you can do with functional programming, what are the concepts and the background of functional programming, and how could something like this be implemented such that you can really execute these languages. So this concludes the lecture on functional programming. I hope you enjoyed it, or at least parts of it, so I enjoyed as well. And if you liked it, then I would be happy to see you again in a lecture. So next summer semester, not the coming semester, that will be the winter semester, but next summer semester I will give the lecture on logic programming, and that is also very nice and fascinating, so maybe you're interested in coming again. Okay, otherwise I wish you good luck with the remainder of your studies and nice holidays.